Hello and welcome back. We are going to look at a really neat way we can find molar mass from osmotic pressure. In fact, we're going to take a substance with an enormous molar mass out of a protein, and we're going to use an osmotic pressure calculation to figure out how heavy it is per mole. So we're going to take 5.87 milligrams of a protein, and a protein is a very large organic molecule. And we're going to go ahead and dissolve it in a solution so that the total volume is 10 milliliters. And we're going to measure the osmotic pressure of that solution, and we're going to find out that it is 2.45 torr, so torr short for Torricelli, at a temperature of 25 degrees C. So this is going to be an aqueous solution, by the way. And that gives us enough information to calculate the molar mass of the protein. So how would we do something like that? So in a problem like that, I normally have no idea how to start. So actually, normally what I do is I just start by writing some equations down and hope that I've got enough information to solve for the missing thing. So in this equation here, I've got the osmotic pressure, I've got the gas constant, I've got the temperature, but I don't know the molar concentration. So that gives me an idea that I can solve for the molar concentration by just taking the osmotic pressure, dividing by RT. Now, the problem with the osmotic pressure is it's in units of millimeters of mercury or torr, and so I have to know how many torr are in an atmosphere, and if you remember from the first semester, there's actually 760 millimeters of mercury. I guess I should write that as torr, right? That's another name for it, per atmosphere. So I can go ahead and I can convert like that. My gas constant is 0.08206 atmosphere liter mole Kelvin. And my temperature is 25 degrees C. That's 298 Kelvin. So here we go. So I got a lot of units here, so I'm going to get rid of torr. I'm left with atmospheres on the top. Let's see, they all cancel with atmospheres on the bottom. What else do I have? I got Kelvin, top and bottom. And at the bottom of my equation there, I can see I've got liters over moles. But of course, since it's on the bottom, when I divide it into one, I will have moles over liters. So at this point here, I've got units for molarity that make total sense. And if we calculate what this comes out to be, I get 1.318 times 10 to the minus 4. And in terms of significant figures, I don't think I can really go past 3. So I'm just going to keep that 8 on the end as a guard digit. All right, so how is that helping us here? It doesn't really seem like it's helping us at all, but we remember molar mass is the number of grams there are in a mole of something. So actually, since that's just a ratio, it's just the mass in grams over the chemical amount in moles, or moles in moles if you prefer. And what am I given in this problem? I'm given 5.87 milligrams. So that is essentially what I can have on the top there. So in milligrams, right? I know there's 1,000 milligrams in a gram. So that's 0.00587 because I'm just dividing by 1,000 grams. So all I need to do now is figure out how many moles I have. Well, I've got the molar concentration. It's the number of moles in a liter, but I have 10 milliliters of my solution. So 10 milliliters. And I can convert to liters. I remember there's 1,000 milliliters in a liter. And now my molarity is the number of moles in 1 liter. So 1.318 times 10 to the minus 4 moles in 1 liter. And so my 10 milliliter sample must have, let's see, what would that be? 1.318 times 10 to the minus 6 of a mole. And at this point here, right, this number here goes up here. So all I got to do is divide 0.00587 grams by 1.318 times 10 to the minus 6 of a mole. You can see I am dividing a really teeny tiny number here into a small number, but that's much smaller than that. So it's going to give me quite a big value at the end of the day. And at the end of the day, I get 4.45. That's rounded to 3 significant figures, times 10 to the 3 grams per mole. So that is 4,450 grams per mole. So that makes sense because proteins are actually kind of large molecules. So to have a large molar mass is probably something I should be expecting. And that's a really neat and practical way. So if you want to know the molar mass of something that's really large, like a protein or a polymer, then freezing point depression and boiling point elevations, you just don't get enough of a difference to see anything. But osmotic pressure is really sensitive and really easy to measure, and a really nice, cool way to find these molar masses. Wasn't that fun?